So actually, who has heard of the paper before coming here? Just okay, so everybody's interested in learning about the paper. So before we can get into the attack, I'm gonna try to explain enough so that we can understand the attack. Maybe show of hands also, like who knows about GKR and like how it works, or who knows about GKR? Who knows how it works? Oh, okay. So one person knows how it works. So you can help me if I say something weird or. All right. To understand GKR, so I think that's going to be the sort of the bulk. That's the proof system. Stands for the letters of the authors, I guess. Funny thing, the attack is from. So the R here stands for. Someone helps me. Rothblum. And the attack is from the brother of the GKR, Rothblum.
Oh,
so
the same guy.
Not the same guy, they're brothers. I learned that the other day. And GKR is a proof system. So as with most proof systems, what you're proving is that you have an output that's a circuit applied to an input. And we're going to see that the circuit that you're using in GKR usually is some circuit that's parallelizable, or it doesn't have to be, but it's better if you can parallelize it because that's where GKR is good at. And I'll explain that in more detail, but basically you'll see that the Y here is an output, maybe an output with like maybe two outputs or one output or something like that. And it comes from, so this is Y, and it comes from X, and X is an input, let's say with 4 entries. And what happens is that we're gonna go from this to this by successive layers. And you'll see that each layer is sort of parallelizable. So, or like what happens in a layers is what happens in parallel. And so that's where we have efficiency improvements. But to understand how this works, spoiler alerts, basically what will happen is that we're gonna go from the first layer, which is the outputs, down to the next layer, down to the next layer, down to the input layer, which is the last layer. And we're going to use the Sumcheck protocol to do that. So before I can explain that, I'm going to explain the Sumcheck. So that's why I have Sumcheck here. And I need to talk a bit about interpolation and Fiat-Shamir before I get into these things. Okay, let's start with Fiat-Shamir. The whole point of this attack is around the Fiat-Shamir, or it's connected to Fiat-Shamir with the scheme. If you don't know what Fiat-Shamir is, maybe I'll write it down. Oops. I'll write it down here. If you don't know what Fiat-Shamir is, basically it's the thing you use to make an interactive protocol non-interactive. And so what happens usually is that you instantiate stuff that looks random, so verifier messages that look random, with a hash function. And so that thing is already very controversial. There's a whole field of cryptography where it's like you should not instantiate something with hash functions because we've proven that some contrived protocols are insecure when you move them from this idealized world to a world with hash functions. And so this is not news, and we already know some protocols like that are completely broken when you instantiate them with hash function. But again, Fiat-Shamir is, if you see an interactive protocol between a prover and a verifier, where the prover is trying to prove something, for example here, that the output of that circuit is Y. Any message from the verifier, which we usually call public coins, because it's public messages and it's random. Whenever it's like that, whenever it looks random, then you can replace that heuristically using a hash function, and it sorts of work. So far, most of the internet works like that, so we're confident that hash functions are good, and Fiat-Shamir works most of the time, and so on. Okay, so now you know enough about Fiat-Shamir. I guess any questions on that? Or and just a note on interpolation also before I go too far. But in cryptography, we usually look at these vectors, or in proof systems specifically, we look at vector of data. as polynomials, because we're trying to prove math. So vector of data are not really mathematical. So we convert that into polynomials, and then we play with polynomials. A vector of data, the way you convert that to a polynomial is that we say we interpolate these vectors. And usually what happens is that if you have a vector like this, well, let's say 4 entries, and this is A, B. You can imagine these are real values, usually in the field, but I'm not going to talk about that, in a big set of numbers. We just said this one is associated with 0, like an array. And so I'm going to create a function such that f of 0 is A, f of 1 is B, f of 2 is C, f of 3 is D. So usually we have efficient algorithms. You do Lagrange interpolation, and you get these polynomials back. And then you can evaluate that polynomial at random points, and that's the sort of things that we do in proof systems. In these protocols, in GKR, the Sumcheck, and everything, the way people implement it is that they don't use univariate polynomials. They use, I'm going to replace that. They use multivariate polynomials, specifically multilinear polynomials, but I don't think it matters too much. But here, basically, because we have 4 entries, we're going to have 2 variables, and we're going to say that we have fx1 and fx2. So this is a multivariate polynomial, right? And we're going to say that f of 0, 0 is A, f of 0, 1 is B, f of 1, 0 is C, and f of 1, 1 is D. So what's happening is that we're using multiple variables to encode the vector, and these variables only take values in what we call the Boolean hypercube, but it's a kind of fancy word that's scary, and it only means that it's a bit string, basically, if you want to think in terms of computer science. So these things usually are multilinear, meaning that if you give values to, so imagine that you have a polynomial with like many entries. If you give values to all of these entries and you only look at this variable, so you give 0, 1, like whatever, then the degree of that polynomial is degree 1. So that's multilinear. And you can think of it will look like x1, x2, plus 3, plus 3x3, I don't know, something like that. But if you have a square here, nope, that's not multilinear. That actually doesn't really matter for everything I'm going to talk about, but it's kind of a TMI if you're interested. Any papers that talk about that will mention the fact that what multilinear polynomials are and these kind of things. Cool, so I think I'm going to talk about the Sumcheck protocol, but any questions so far on any part here? All good? All right, so how am I going to, okay. So the Sumcheck protocol, I'm going to write it down here. Basically allows you to compute a sum, or to prove to someone that a sum is equal to something. So maybe let's take my polynomial f as example. F, maybe with less variables. And here I'm going to prove that this is the fancy notation. Here I'm proving that the sum of that polynomial over what we've seen as the Boolean hypercube is equal to h for a given h. And maybe this is easier to see like that, but what I'm saying here is really, plus up. Ooh, that's my phone. So does that make sense to everyone? I'm computing that sum when all the variables can take anything from 0 to 1. And for some reason, it's useful, you know. I don't know how familiar people are with the Sumcheck because I didn't ask. But for some reason, it's very useful in a number of proof systems to use this Sumcheck. Like Jolt used that, Hyperplonk used that. You see it in like lookup protocols. You see it in a bunch of different places. For some reason, they managed to reduce a problem to proving that some value h is equal to a sum of that polynomial. Yeah, trust me, it's useful. So, okay, so now I'm gonna explain to you how that works. You know, assuming it's gonna be useful afterwards, I'm gonna give you an intuition of how you can prove that to someone. And think about it think about it from the point of view of a verifier. You don't want to compute that sum yourself as a verifier or as, you know, as yourself, because it takes a lot of time to compute that. You want to do that, you want someone to prove it to you. So the whole protocol is not necessarily, at this point in time, we don't even care about the privacy, we just care about doing this efficiently. And privacy and zk and these kind of things usually sort of comes for free at the end. So what we do is we start, how does that work? Maybe let me make some room. Okay, we don't need this anymore. So the first thing we're gonna do, so again, we're looking at an interactive protocol. And later we can make that protocol non-interactive using Fiat-Shamir, and that's why it's tricky. And the first thing that the prover is gonna do is that they're gonna send, how can we call it? We can call that, I don't know, G1. They can send a polynomial to the verifier. And the verifier will do two things. They will check, well, actually, they will do one thing first. They will check if J of 1 of 0 plus J1 of 1 is equals to h. Let's, so this is weird, right? But this is true. You know, they will think it's valid. Like the prover has proven that fact here. If G1 is if G1 is the sum, or f the x1, x2, x3, where only x2 and x3 are part of that Boolean hypercube. In other words, we have f x1 0 0 plus, maybe I'll write here, plus f x1 0 1 plus f x1 1 0 plus f x1 1 1. So okay, I'm gonna say that again. Maybe it's not super clear. The prover sends a polynomial to the verifier. The verifier checks if that polynomial at 0 and 1 added together is h, right? If it's not h, they stop. And this is enough to convince the verifier if the polynomial G1 is computed as this sum. Do we agree or do we disagree? Disagree? No, just kidding. Okay, so unfortunately, we don't know if G1 is of that shape, right? We have no idea. The prover could be lying to us. So what we're gonna do is that we're gonna say, okay, prove that to me, but prove it to me at a random point. And if you've heard of Schwarz-Zippel lemma, the Schwarz-Zippel lemma before, if you prove it at a random point and these polynomials are of low degree enough, then it's fine. With high probability, this is secure. And I guess I've explained it so many times, I don't want to explain it here. So if you don't know what it is, just Google Schwarz-Zippel. And I'm also not going to write it down because I always botch the spelling. So ask someone and then Google it. But basically, the verifier is going to try to do that. J1 of R for some random R, and it's going to check if it's equal or not to this sum here, right? Well, I'm not gonna, I'm not gonna rewrite it up. R here, I made a mistake. Yeah, I'll do it cleanly. Okay, up. So at some point R. Right, so I don't know if this is convincing what I said, but if the verifier can check this equation at a random point R, and these two things are equal, we have a polynomial identity, then they can be assured with high probability that this is G1 was formed correctly. And so I don't know if you noticed that, but this thing is a sum, right? It's kind of like H. It's a value that the verifier can compute. And this thing here is a sum over a multivariate polynomial, actually a multilinear polynomial, but doesn't matter too much. And so we have the same problem that we had previously, right? This proving that some value is equal to a sum of a multivariate polynomial is exactly what we're trying to solve in the first place. So if you're convinced by that, oh yeah, and by the way, the challenge here, you know, this is random. I guess you can write it like that, say that it's random. Oops. If you're convinced by that, you know exactly what's happening next. What's happening next is that the prover sends a polynomial G2, and then the verifier checks, I'm gonna go here, the verifier checks if G2 plus G1, G2 of 1 is equals to this thing here. So maybe I'll use that. And if it is equal, we just need to convince the verifier that G2 is computed correctly. Okay, did I convince people here that this works? So what does the verifier do next? Maybe let's see.
Constrains the next variable with a random choice.
It what?
Chooses another random, sends that as
Oh yeah. So it chooses another, let's call it R2. And then you do the same. You evaluate G2 at this random thing, and you check that it matches the last thing, the polynomial evaluated at R and R2 here, right? So maybe a better question is, what do you end up at the end?
Value at a random point.
Right. So at the end, if everything went well, we end up with so we reduce the claim, right? We say this is correct if G1 is correct, and we said this is correct if G2 is correct, and then we said this is correct if whatever we have at the end is equal to F1 F with all the random values, and we'll have 3 random values at the end. And at the end, the verifier knows that the sum is correct, this H is correct, right? If this thing is equal to like something that they computed as part of the thing. I could go over all the steps, I guess, but I think every step looks the same until you instantiate all 3 variables. And this is very efficient to compute yourself as the verifier, right? It's not like computing a sum. You just have to evaluate the polynomial. Or in some protocols, you'll have like, maybe you have a commitment to F, so you get an evaluation proof that F is evaluated correctly, depending on the protocol. And yeah, I guess that's all there is to the Sumcheck. Yeah.
Isn't there one more thing that you have to check that's about like the degree of the function that's being sent to you, G1? I forget what.
Yeah, so I guess if you send G1 and it's of like a very high degree, this is not gonna work. So you probably want to like upper bound the degree of G1. But here I'm only talking about completeness. I'm not talking about how to make the protocols. Well, I guess I'm talking about both, but yeah, this is definitely something you'd want to check. Yeah. Okay, so this is the Sumcheck. Again, in a few, in a number of rounds equal to the number of variables in my polynomial, I managed to convince a verifier that for some given number, it's equal to the sum of that polynomial when evaluated over all the combinations of 0 and 1 for variables. If that didn't make too much sense, it's okay, because I'm only going to use that fact afterwards, and you can just forget everything here. And if you, I have a video online also where I explain this in the same way, if you want to, or this is going to be published, I guess. But any other questions on the Sumcheck before I go to GKR? All right. Maybe I'll leave this one here. All right, let's go to GKR. So GKR, as I was saying, there's different layers, and you're trying to prove that an output layer came from an input layer. And the output is, I'm going to take the example with 2 outputs. You can do more, of course, you can do more outputs. But this is what the attack does, and so that's going to be useful for the rest. And the input, I don't know, we can see a vector of 8 entries, for example. Doesn't matter too much for my explanation. And I said that we have different layers, and you can see the different layers as vectors of values as well. And basically what happens is that in your circuit you'll have, I don't know, these two are added together to give this thing here. This thing here is a multiplication of this and this. You're a circuit, right? So you can do anything you want. In the original GKR paper, they have 2 gates that you can use, addition and multiplication, but you sort of can do whatever you want. And basically, this is the description of your circuit. The number of layers and what happens in a layer is the description of the circuit. The other thing to know is that, as I said with the interpolation part of my explanations, this is you can see that as a polynomial. I don't know, let's call it F1, I guess, where multivariate polynomial. So here there's only one variable. When F1 is evaluated at 0, then we get this variable. When F1 is evaluated at 1, we get this variable, right? And here you have some input polynomial as well. So if this is F2 and F3, this is F4. And now we're gonna think about how can we make this problem look more like the Sumcheck. Because I said the Sumcheck is useful. Okay, why did I explain the Sumcheck? The thing to notice is that we can express this polynomial here actually as a sum over this layer here. So let's call that F2. And so the way they do this is, maybe I can give some intro before I get there. So imagine that you have an addition gate, right? Imagine that F1 of 0 is F2 of 0 plus F2 of 1. This will correspond to this. Oh, actually F2 has 2. Whoop. This will correspond to these 2 added here, right? So how can we have a sum that sort of looks like F1 of x equals sum of x2, x3 over the Boolean hypercube? How can we have something like that? So I'm going to tell you the answer. I'm not going to let you think about it, but it's not that complicated. Actually, if you add another extra polynomial that we'll call add x, or let's call it x1, x1, x2, x3, and you multiply it with your sum, f2, x2, x3, plus f2, what am I doing? I'm gonna need more variables. Yeah. X2, X3. So actually, the way I'm going to do this, I'm going to use vectors. It's going to be easier because there's going to be too many variables otherwise. Something, let's call it S. So imagine this is a vector, but we have two variables in there. And this is another vector. But you can imagine that this is like x2, 1 and x2, 2. If that makes sense. The reason why I'm doing this is that I want these two variables to represent one entry in that vector, and I want this vector to represent another entry in that vector variable. And then I want add to tell me for these outputs. Maybe it's easier. Like the way I think about it is that these are not really variables, but they're indexes in like for my array. So when I think of x1 here, if I set it to 0, it's going to be the first index in my array. If I set it to 1, it's going to be here. And x2 is like either 0, 0, or 0, 1, or 1, 0, or 1, 1. So I'm sort of indexing in my array. And this thing is going to basically be, maybe I'll use different color. This is going to be what other protocols call a selector polynomial, I guess, where this thing, it's going to be 1 if you want to use the addition gate, or 0 otherwise. 1 if you want, out, maybe in a computer notation, x1 equals in x2 plus in x3. I don't know if this is more confusing than just staying with math, but you can sort of think about a program where this thing just tells you if you have an addition or if you don't have an addition. Yeah. So if you understand that, you can sort of look at that and you can see that this sum should indeed, tell you that, should indeed give you the proper value for that according to the description of our circuits. The circuit is described by the values of that add polynomial. Is that convincing? Maybe I'll stop for questions. Yeah?
So that, you mean that the add polynomial could have like a full table of like, if these are the different inputs, this is the result, and that would describe the full circuit? Yeah,
I guess there's a truth table for that. You can see it as like the outputs and input 1 and input 2. And then, the actual value of your polynomial add. And for the output 0 and input 0 and input, for these entries, maybe you don't have an addition. And so you can go through all of these possibilities, and maybe you have an addition for the, I don't know, maybe this entry here, so 1, is the addition of like 0. Remember these are vectors actually, so 0 and 0. So 0, 1, and 1, 1. And maybe we have a 1 here, meaning that these two entries are added together. Does that connect to what you were saying?
Just to check, like, when you say that it's a vector, that would be like in the second row and at position 0, 1.
Yeah. Yeah,
and the next one would be, or like 0, 0 is the first one, 0, 1 is the next one.
Right.
1, 0.
This is 0, 0. This is 0, 1. 1, 0. 1, 1.
And V being 1 just means that there is a gate there for addition.
Yeah. Because when there's 1 here, then it's going to be multiplied with this addition, right? When there's a 0, then we're canceling the addition. And you can imagine that the same thing is being done with multiplication, like in the first paper. I don't know, you want to give me the multiplication? So you can imagine there's a plus.
Plus mole.
Yeah.
x1, x2 vector.
Right.
x3 vector. and then that's multiplied by. So that's your selector. That's multiplied by x2 times, f of 2 x2 times f of 2 x3.
Right. Yeah.
Cool.
Okay, cool. So this is basically where just as a recap, we have a polynomial here to represent the outputs, and we have a polynomial to represent the next layer, which is an input that came before, or an intermediate temporary values, I guess, in your circuits. And we have a formula to represent these values, right, as a sum using this polynomial. And so this should look like something that's familiar to us. What does it look like? The Sumcheck, yeah. The Sumcheck, right, where you have a given value and you have a sum of a polynomial and you're trying to go over the Boolean hypercube. So,
like, where is the x1 in the entire circuit?
Where's the x1? Oh, I guess that's the x here. Yeah, I gave it a name. Cool. So that's not enough. There's one last trick, I guess, to GKR. It's and we're gonna basically use Schwarzschild again. We have this polynomial here that represents this vector, and we want to prove that it's the sum of this thing. To prove that, we're gonna basically prove that it is true at some random points. Right? So we're gonna say, nope, I don't want the polynomial, I want that at some random point, and I'm gonna call it G, because that's what they call it in the paper. If you look at the paper, you can follow that. And so it's gonna be a G here, and now we have, and this is the H. If you remember, I called it H in the Sumcheck. And so now you can just go with the Sumcheck protocol. Right? So the first step is that you look at this instance, you create a random value G to obtain this H, to evaluate the output layer to G to get H, and then you do the Sumcheck with this thing. If you do the Sumcheck with this thing, it should tell you that basically this layer is correct. And then what you do when you reach this layer is that you do another Sumcheck to reach this layer, and you do another Sumcheck to reach this layer, and then this layer, you know it as usually as the verifier, so you can compute that yourself. I'm gonna repeat that because it's not super clear, but at the end of that Sumcheck, what do you get? Okay, someone tell me actually. That's a good test. What do you get at the end of doing a Sumcheck with this thing?
Claimed evaluation of f of 2 at a random point.
Right. So yeah, so you get f of 2 at a random point x2, right? So we're gonna call that R2 maybe. It's a vector. But this one is different, right? So we're gonna actually get two claims. So here, I'm not gonna talk about that, but there are optimizations. So here we end up with two claims. These, we don't know how to evaluate that as the verifier, because we don't have access to these intermediate layers. We don't have access to the inputs or the outputs. So what we do is that we say, okay, sure, these are, evaluations, but let's do a Sumcheck. Since I have another formula for this thing here, let's just do a Sumcheck using these things. And then we end up here, we have like another Sumcheck to do, but basically we don't know these values. But at the end, we'll have an F4 that we can evaluate on some random variables. And so the optimization here is that you can sort of combine these values into a single value to not blow up, so that you don't have every, at this layer, then you have 4 different Sumcheck that you need to prove. Okay, this maybe was trickier to understand, but it doesn't matter because none of this matters to understand the attack. But if you want to understand GKR, this is how GKR works. Okay, I'm gonna move to the attack now, but the nice thing is that you can sort of forget a lot of these things to understand the attack. And so if you fell asleep at some point, then you can wake up again.
Are you doing Sumcheck once between each of these layers and then like maintaining your random choice for those?
Right. So at the end of at the end of this Sumcheck, we get this, and this is basically like this evaluation. But this one we did at the start. We don't have we choose G, but then we never do that again. We always get this for free, I guess.
Okay.
Does that answer your question, or?
Yeah.
Yeah. But you know, if you implement it, you can see that clearly. Maybe you want to do that after. It's a good exercise. Okay, any other questions before I jump to the attack? And okay, cool. Okay, so maybe I'll leave it like this. So basically, if you look at the paper, there's like 3 attacks, and it just gets better and better. The first attack is enough to understand sort of how the other ones work. And what they're gonna do is that they're gonna figure out a circuit such that when you instantiate this GKR protocol that we just looked at with Fiat-Shamir, so you know that first G that we got from the verifier is basically gonna be a hash. You know, G is gonna be a hash over. Maybe I'll write hash since I've used H. A hash over the output, and usually you have the input as well. And the circuit itself, or like a hash of the circuits, maybe. And that's how you get this, right? Like you hash everything and you get that's how you do Fiat-Shamir. So they're gonna basically find a circuit such that they can lie about the output. And I'm gonna give you the example that they give, it's a good one. They basically choose an output that's 0, 0. It makes it easier, but you don't necessarily have to choose an output that's 0, 0. But what's nice when you choose that output is that, what's gonna be the interpolation of 0, 0? Someone tell me what polynomial represents these 2 entries? 0. So we have the constant polynomial f1 is just 0. So in the protocol when I'm gonna get G, and I'm gonna evaluate that at G, it's gonna give me 0. That's not how the attack works. I mean, that's not the trick of the attack, but it simplifies how we see the attack. So we remember, right? As the verifier, you're gonna evaluate that at G, right? So we get the first thing that happens. Well, that's the first thing that happened, let's say. We produce G, and then we do f1 of G, which is gonna be equal to 0. And I told you that in this attack we produce a different output, but this is what the verifier thinks that we produce, right? So what happens is that the circuit actually goes here and produces a different output, but we have to convince them that it's these outputs. Meaning that we have to convince them that this polynomial, when evaluated at G, is also 0. So we have to produce something that when evaluated at G is also 0. Let's call it like that. Although this one is the malicious one, so we'll invert it. This one is the one that is not produced by the circuit. This is the fake output. This is f1. Okay, so how can we find a polynomial that is not 0, 0, and when evaluated at G is 0? Well, the harsh, truth is that you need to know about G. There's no other way around. Since G can be any random value, and we're in a field, which is a set with huge amount of numbers, we need to know about G. But what we can do is that we can actually compute a circuit that computes G itself, because the G is computed as a hash of all these things, where actually G is computed as a hash of the wrong outputs. We just need to create a circuit that implements this. And that's basically the whole trick about GKR, is that they compute a circuit that implements this, and then there they put what is it? They create something such that f1 of x equals x minus g, right? So they put minus g 1, right? So f of 0 is minus g, and f of 1 is, what am I doing? Wait, so we want 1 minus g, right? So, yeah. So that's what they produce, so that we have x minus g, right? They actually don't do that in the paper. They do they do it another way. But this should work also. Does that make sense? Did I make a mistake? So they compute this polynomial. At 0 it's minus g, and at 1 is 1 minus g, right? And so we do have f1 of g is equal to 0, right? So as you could see, you don't really need to understand what's happening here. You just need to understand that the start of the protocol, you just produce a random value g, and since we can actually produce it in the circuit by providing the right inputs, we can produce it in the circuit. Does that make sense? Is that, you don't really need to understand the Sumcheck, or you don't really need to understand GKR. You just need to understand the first layer of GKR, right? That Schwartz-Ziegler thing. And you need to understand GKR allows you to build whatever circuits. So then I'm going to briefly mention the second attack and the third attack. But I just want to know, any questions on this one?
Sorry.
Whoever.
Is there some clear, easy way to because C is in G.
Right. But you have to imagine that this is like a digest of the circuits.
Okay.
So it's a hash of the circuits. And so you can pass that as witness of the, you can pass that as inputs. Because we didn't know what the circuit looked like at this point, right? So this we don't know what it is, but we can pass that as input to the circuit. So we can have a circuit that computes this thing on any output and any circuit description. Is that what you were asking, or?
That the circuit knows itself and can calculate a hash,
right,
is the part that wasn't immediately clear to me.
Right, so it doesn't need to know itself, because here we can just pass it as inputs. When we created the circuit, we didn't know what this thing was. That's correct. And by the way, this sort of recursion, right? Like the circuit doesn't know itself. How can you compute in all the recursive verifiers, like when we do recursive zero-knowledge proofs, we always have to do things like that. We don't know in advance what the circuit looks like, yet it can verify itself, and this is because we can pass a shorter description of the circuit afterwards as inputs.
Using G, we basically find out F1 prime, which is 0, right? In the second step.
F1 tilde.
Yeah.
I don't know how to say it. Or squiggle, I think. So what?
We find that polynomial where evaluated at G, that is equal to 0, right?
Right, so the easy way was just to do 0, 0. But yeah, essentially I think the attack generalizes and you can do any constants. And even if you didn't have a constant polynomial, I think you could just pass that as inputs. And in addition to generating G, you could also try to evaluate that as well, if that makes any sense. So you can think of this example that I gave as a very simple example for the attack, but it seems like the attack generalizes to any sorts of outputs. Yeah. Does that answer? Yeah. All right, we can take it offline otherwise. Yeah?
So the primary thing is contingent on, the attack is contingent on is G being derived from a concrete hash function, right? Because if it's not derived, you can't figure out G and you can't do the entire.
Okay, so I guess that's a very good question, because this is, if you don't know the hash function here, basically that's the third attack in the paper. And they say that they have this notion of adaptive attacker, I don't know what. Basically, if you this attack doesn't work if you don't know the hash, but you can be, I never remember who is adaptive, if it's the verifier or the attacker. But in any case, there's a non-adaptive or an adaptive attack where you can even if you don't know the hash, you can basically do the attack. And I'll explain that, I guess. So, well, I'm not going to explain exactly how that works, but I'm just going to give the intuition. In the paper, they say, okay, you might think that this is kind of useless because it's only on circuits that implement that hash here, or that very specific thing. So they sort of generalize this thing, and they're like, well, actually, no. If your layer here is like a sort of a if then else function, if you implement that as the last series of gates, I guess, you can sort of switch, and you can say, here I want to do the attack, or here I want to do the normal functionality of the circuit. So this basically becomes your backdoor, and then there's another side of your, if we split this like that, there's another side of your GKR that does, it's a ZK rollup maybe, or it's like whatever application you have in mind. So that you can like activate your backdoor or just do it normally. So the second attack is basically sort of explaining that you can target like a different layer, I guess, by hiding your, at least that's the way I understand it. And maybe I'll mention the third attack. So what happens if you don't know the hash? So, and this is very theoretical because like usually you know that function, like you don't need to adapt to that. So I don't think that third attack really matters. But basically they say, well, if your GKR circuit implements a zkVM, then you can pass the program that implements your hash. It's a VM, right? And so you can execute whatever you want in your circuits, and so you can do that. Does that make sense? So if you have a zkVM, then you can pass any type of program here, and that program could be this thing here. At runtime, when you're trying to use the VM.
Oh, so it's the same intuition of like passing the circuit to itself, except this time you're passing the hash to the VM itself and generating the same.
Yeah. I think you can sort of see that way.
Yeah. So you still get G that way by passing the hash function to the VM itself, right or no?
Wait, say that.
Like by passing the hash function to the VM, do you still get G, or is it like are steps 2 and 3 roughly the same? So
by passing the hash function and computing that program also, yeah. Right? And passing also the description of the program, I guess. So you'd have to, it's a very theoretical attack. So it's like, it should work if you use a VM. But yeah.
You're saying, like if it's not doing this hashing, but it's a VM, you can just pass a program that is doing this hashing.
Yeah. And your VM will run it. Yeah. But again, it's not very important. It's the main attack is this one, I think, where you can sort of hide a backdoor to lie about your outputs, or have like a normal behavior of a circuit. So that's about it. Hopefully that makes sense. And maybe the question is like, is that something we should be worried about? Like, is everything compromised? Should we use GKR? Should we continue to use Fiat-Shamir? And I guess it's a nuanced answer. Like different people might have different opinions. But one way that this attack works is that it really relies on the fact that you can have like embedded circuits inside of your protocol, so you can sort of like run stuff before you even get to the end of the protocol, which is kind of weird. There's different reasons, I guess, why this attack works, but also it's sort of contrived. You'd think that someone would notice if there was such a backdoor, which is what I'm thinking about. I don't think we should really be too worried about that, but it's definitely possible as these things get, commoditized, and when people use NPM and they have like millions of dependencies and these kind of things, maybe there's a dependency that could be backdoored and sort of modify your circuits in this way. And so maybe we're screwed, or maybe not we're screwed, but maybe we will see someone try to exploit this kind of vulnerability in the future. But I feel like if we audit these kind of circuits, we would see that pretty clearly. But nonetheless, it's a very interesting attack. And it is interesting in a way that's very practical. And this is not theoretical. This seems very practical to implement. But yeah, I'll leave it at that. If you have more questions, I guess we can take it offline, or I don't know, maybe we want to record them. I don't know how much. Should we cut it here, or?
Probably.
Yeah, okay, let's cut it here. Cool, thanks. Yeah.